Good morning, everybody. My name is Barbara Pogorzelska. I'm originally coming from Poland, from Szczecin. It's also a city on the coast, but Gdańsk is better. You have the coast. We have to drive 1 hour by car to get to the coast. So great to be here in Gdańsk and great to see you here on Saturday in the morning. I hope your chairs are comfy so that we can start and you still feel, relaxed on Saturday. Okay, some introduction to what I'm doing at Amazon. I've been with Amazon for 5 years now as a software developer manager. Originally, I joined in a core ML organization. We developed a service that went into SageMaker, so we launched that together with the SageMaker 2 years ago. And after that, I transitioned to Amazon Search. Amazon Search is an organization that basically matches your query results with the product. So when you look for Nike shoes and type Nike shoes, that's all what you see on the Amazon page is basically owned by us. Okay, but today's talk is about AWS and AWS SageMaker. So let's start with that. I will start with 3 questions to you. So how many of you have used SageMaker before? Okay, few. How many of you have some basic knowledge in machine learning? Okay, roughly half of you. And basic knowledge in computer vision? Okay, some. I will try to use that knowledge to adapt a bit the presentation so that you all feel informed about what's happening. So I will give you an introduction to SageMaker. Then I will give you an introduction to computer vision, so basically basics that you need to know to understand the example. And I will give you some introduction of the frameworks that I will be using during the demonstration. So let's get started with SageMaker. SageMaker was built to make it easy and quick to deploy and to develop machine learning algorithms. So we have at Amazon, but also outside of Amazon, we are thinking of how long does it take when you have a data and you have a problem and you want to develop machine learning application, how long does it take to basically bring something into production? And the average cycle takes between 6 to 18 months. So it's long process. So basically, you collect the data, clean the data, then you train your model, then you make some iterations because the first model does not work that well. So you do those cycles, and in the end, you are happy with your model and you want to deploy it and use it in production. So let's say, I don't know, you have a prediction of the clicks. So you are in an advertisement business, you predict your clicks. So it takes, long time to bring something into production. And that's why we said, okay, that's basically the same problem we have at Amazon. We have tons of machine learning, computer vision experts, and it takes them long time to bring something into production. So we need some platform, and SageMaker is the answer to that. So what are the building blocks of SageMaker? So SageMaker is very modular. So basically, it's already the second version of AWS service. The first one was Amazon Machine Learning Service, which was not that flexible. So we said, okay, we need to have a flexible service. We need to address every step in the development process. So we start with the user interactions. Then we go to the model training, hosting, and basically whatever goes together with that. So all the algorithms, all the possibilities to train models, and into something that's really close to my heart, the hyperparameter optimization. That's basically the service that my team developed and launched in SageMaker. Okay, so let's start with the first building block, which is the user interface. So how can we work with Amazon SageMaker? We start with a very, very simple use case, which is basically you have your data, you don't need to clean the data, pre-process the data, you just take it. You take existing algorithm, you train the model. So the model in machine learning means that's already algorithm that has seen the data, was basically adapted it to the data, and has now the capability of being able to produce some input. So if you think of a forecasting model, so let's say you do forecasting prediction for, I don't know, demand on the product. So you want to predict how many of your shoes, if you have a shoe store, how many of the shoes will be will be solved in the next couple of weeks, days, whatever. So you say, OK, I have my past data, so I have my selling data from the past. And I have an algorithm that's meant to basically forecast my demand for the future. So I adapt the algorithm, so I train the model based on the data. So I've seen the data, and I adapt the model in a way that it fits the data. So that's the couple of terms that we are using in machine learning. And after I basically have seen the data, I iterated over the algorithm, then I have a model, and then I can use it in deploy. So basically, the third option that you see here is the SageMaker console, which is basically you can click through the, you have the data. I store my data in a S3 bucket. I will take some algorithm that's already existing in SageMaker. I connect the two. I take some instances, so EC2 instances, the compute instances that will be used to produce the model. Then when I have the model, I can just click it and push it into inference. So inference is real-time inference or batch inference, and that's basically it. So with a couple of clicks, you can build the entire pipeline. With the caveat, it's like meant for simple use cases. So generally, those use cases are a bit more complicated. So what the first option you see here is what normally scientists do is they have I would say, an environment that we call, it's like the mostly used one is Jupyter Notebooks. That's an environment where you can explore. So basically, it's a notebook where you can just download your data and explore the data. So look into the data, type some code, some lines of code with the cells, and then execute it on demand, see what's happening. And when that's fitting, then you can basically go and train your model. Apache Spark is a framework for distributed data processing. So in all applications where you have many, many gigabytes of data, or rather terabytes of data, you need distributed processing of the data. So Apache Spark is basically, 3 years ago, it was the mostly debated topic in all machine learning conferences. The last option that we have here, basically you can build that on your own with your computer, with your system, whatever, and then use it in SageMaker as well. Next topic, so next module is the training. So how does it work? So there are also several options for the model training. We have in SageMaker built-in algorithms that you can use out of the box, just picking them and training on your data. The next one is, if you use already Apache Spark, you can just take the Amazon SageMaker library, use the APIs, and call it from Spark. The next one is the commonly used deep learning frameworks and machine learning frameworks, TensorFlow, the one from Google, and MXNet. Both are open source. They are also integrated in SageMaker. And the fourth option is build your own Docker container. So basically, that's the tech. So whatever you have, you can push into a Docker container and then push the container to SageMaker, and that magically works. Hosting. Once you have your model and you have, I don't know, let's have an example. You have an application where if customers are clicking, you want to basically respond on the fly using your model. So an example of that would be, let's say, advertisement. You have an app, and there is an advertisement, and the advertisement is using some content, so some content from the app. And you want, basically, whenever a customer is using the app, you want to have some different content showed in the app. And this one is basically powered by a machine learning model. So you have your model, in the Amazon SageMaker inference, and that's connected with your application. So that's basically you get on the fly the responses there. There are also some other aspects of Amazon SageMaker that are using in some of the building blocks. So if we think of algorithms, they are using, so the same algorithm or the same frameworks are using in training and in the hosting mode. So basically Amazon AWS developed models and algorithms can be used. You can use the distributed frameworks available, and you can bring your own stuff. And the hyperparameter optimization is something that's a step that you can connect between the UX and the model training. I will have some slides on it later as well. Okay, let's start with hosting. So what does it mean to host? So basically, once you have a model, machine learning model, your forecasting model, then you need to push it to the endpoint. So, and you can do that with one click. You pick the instance you want to have the endpoint on. You pick the number of instances that might be basically based on your requirements. The latency requirements, the CPU requirements, and the availability requirements, whether you want to have in different availability zones or in one place, it's okay, based on your business. You pick that and you have. So one very, very important and useful feature in Amazon SageMaker is the A/B testing. So what does it mean, A/B testing? It means you have different models. Those different models are based on different data. So let's say you have one model that has data collected in 1 year, and that's tons of data, and let's say it's very, very expensive to train that model. So you have one powerful, expensive model, and you have also one model that may be trained only on a data that's collected during 1 month. So it's easier to train, and it's cheaper to train, but you don't know how to compare the two. So which one is performing better? So what you do A/B testing. It means you push both of the models into production, and you just put some traffic on one model and some traffic on the other model. So you basically divide your customers into whatever ratio you want. It can be 50-50, it can be like 10% to 100%, and then you test your new models and you compare the two and you think, okay, the one expensive one, is it worth to do the expensive one, or is it okay to basically retrain every month, only with a month, batch of month of the data, and then you say, okay, I have mine, and I'm deciding that I will pick the one that fits my model better. The last option we have is you may have your data somewhere stored, I don't know, some security, so your company is not allowing you to bring your data into the cloud, which means you have to train the model in your infrastructure, and when you have the model, you still can bring the model into SageMaker, just host it, and that will do the job for you. Okay, so we are now going to algorithms, the choices of the algorithms. The first choice is the algorithms that's developed by AWS. So why do we develop algorithms? Because we have tons of data. Normal use case is all the frameworks that are available are mainly developed by researchers and then by companies. So whenever the company has a bit more different requirements on the data, then they can develop their own algorithms, and that's what we do at Amazon. At Amazon, we have tons of data, so we develop our algorithms to be able to cope with the data, which means we rarely use the entire chunk of the data that we are pushing to the algorithm rather than we are using streaming. So basically, we are providing our data chunk by chunk to the algorithm. What we have supervised learning, unsupervised learning, and some more special use cases. So what does it mean, supervised learning? Supervised learning means you have data with what we call labels. So data with labels in our example today will be object detection. So you have an image, and the label is saying, this image is showing a cat or a bird or whatever. That's supervised. So you have the knowledge in the data what the data is about. Unsupervised learning means that there is no label. So basically, an example of that will be customer groups. You have some customers, and you have some specifics about the customers, but you don't know basically how many clusters of those customers. So you want to send an advertisement, or you want to send some offers to some groups of customers, but you cannot by rule specify what are the groups of customers. For this use case, we are using unsupervised machine learning methodologies, which means you just throw the customers with some information about the customers into an algorithm, and the algorithm will recognize how similar those customers are and group them together in different clusters. So the methods here are k-means, PCA, but that's not super important. So basically, once you know your problem and once you start, you can just read and check, okay, what are the algorithms that are available? There are several of them. There, new ones are coming. For the supervised ones, the mostly used ones or the very performant ones are random forests. So it means that random forest comes from a group of trees. A tree is basically a decision tree. So you have on every node you have one decision saying, is the customer, let's say, has the customer some order in the last month or not? Yes, no. So you go to the next node. And if you group all the trees together, you will have a random forest, which means you have different results on every forest for the prediction, and you can average them, combine them. That will, somehow make the error smaller. And for the more sophisticated ones, we have several algorithms on computer vision and on text, on data that's consisting of text. So it's like topic modeling, translation, word-to-vec, and so on and so forth. Okay, the next one, so you can use TensorFlow, MXNet frameworks that are already available. So what you normally do, you spin off your Jupyter notebook, then you load a bit of the data, you do some computation on a bit of your data because it takes forever to train on the entire data, and once you are happy with your model trained on some of the data, you basically use the same algorithm, the same code to have the entire data processed, and then you push it to the endpoint. Okay, bring your own algorithm. Whenever you have some algorithm trained before, you can just pack them into Docker containers, and you can bring them on to SageMaker and host them on SageMaker. So you pick your preferred framework. That's really everything that can go into the Docker container. Hyperparameter optimization. So what does this mean? It means, why do we use the fancy name hyperparameter? Because in machine learning, we use the word parameter for something else. So we use the word parameters for something that we train. That's why the word is basically occupied. So for like normal parameters, we use the word hyperparameters. And what does this one mean? It means that whenever you start building a machine learning application, you have to choose and pick some parameters. And depending on your choice of the parameters, the output could be better or worse. And some of the choices can be very bad, and there are sometimes only few choices that are very good performing. The problem is, if you have multiple hyperparameters and you have multiple values for the hyperparameters, then you build a matrix, and you are not able to check every configuration of parameter, every possible value of all the hyperparameters. What do? You basically build optimization machine learning layer on top of machine learning that's optimizing the hyperparameters. I would say that's something that's a bit more advanced topic, so we will skip this. Okay, let's go to the computer vision example. What do we need? We need data. So we use CIFAR10 data. It's a very popular data in computer vision. It's freely available. So if you look for computer vision algorithms, computer vision methods, then tons of them are using either CIFAR10 or CIFAR100. The 10 is coming from the data is image data. Every image is 32 times 32 pixels. And you have 10 classes. So the classes are airplanes, cars, birds, cats, deers, dogs, frogs, horses, ships, and trucks. It's mutually exclusive, so all the classes are very different. So in trucks and cars, you won't have like pickup trucks or so. So you will have rather, the normal cars and like big trucks. You have 60,000 of those data points, and they are split in training data and test data. Training data is 50,000 examples, test data is 10,000 examples. Something more to say about this one is those are coming from, which is pretty common in machine learning, are coming from a set of 80 million data points where they ask students and paid students to just label them. So the students were clicking, that on the builds, on the pictures, and saying, "Oh, I think that's a car. I think that's a cat." So for humans, it's a very easy task. So no mistakes there. For algorithms, it's not that easy. What we will be using in computer vision is what's called CNN. CNN is convolutional neural network. It's just a fancy name. Normally, neural networks are built like they have layers. So you have your input data, and you connect every attribute of the input data with some node, and then it's like you stack those layers on top of each other, and you connect every point with every point. Why does not work in computer vision use cases? Because imagine an image which is, not 30 times 30 pixels, but let's say 1,000 times 1,000 pixels, then you will be having like 100,000 data points in only the one image. And if you have some nodes in the next layer, and you connect every pixel with every node to the next layer, then you have millions of connections. And what those algorithms do, they learn what's called weight. It's just the size, or maybe the weight is a factor on every edge. So if you would need to learn millions of factors for every layer, and you have several layers of that, you will be learning, or like learning means estimating millions of weights. And you probably don't have even millions of data. So you have only, in this example, you have only 60,000 of data points. So based on 60,000 data points, you cannot estimate millions over millions of weights between the connections, so the connections. Otherwise, you will be just fitting in. So what those algorithms are doing that are complicated mathematical functions, they will just fit into the data. So they will predict perfectly on your training data set, but if you take some test data, they will do the job pretty poor. So what do the convolutional neural networks do? So what the scientists came up with is convolution is just a fancy name for mathematical operation. You will see a lot of fancy names in machine learning. Because it's done by mathematical people with a good of mathematical background and statistical. So it's taking the image, and it's taking a frame and sliding the frame across the picture. So you will see here on the robot. So the frame is basically on the hand of the robot, and the slide, the frame, that's what we call filter that tries to recognize. So basically, there will be one filter that tries to recognize a hand, or another filter that will try to recognize an eye, or another filter that will try to recognize an edge in a picture. And you stack those filters together, so you will be able to basically say, oh, I see an eye here, and an eye here, and maybe an eye here. So I don't know, a creature with 3 eyes, whatever, in the picture. Or, multiple eyes, so multiple people in the picture. And that's basically how you do it. So you don't connect every point with every point. You just have a slide. You have the magic mathematical function, which is named convolution, and it's calculating one value. And that's done for the first layer. What you can do afterwards, you still have many data points, so many estimations that you have to learn. What you do is what's called here subsampling. In convolutional neural networks is oftentimes used pooling It's very, very simple thing. You have another frame, and you slide that across your data, and you have like some mathematical operation like maximum or average. So you take the frame, you see all the values in the frame, and if you take the max, then you take the maximum value from the frame. That's a magical thing that's works pretty well. And basically, that's how the convolutional neural networks work. They stack all those layers, those filters, and they do some subsampling, then they do some other filters, and then subsampling, so several layers of that. And in the end, they basically flatten everything into one big arrow, and they make it smaller in some steps until they reach the output. So the output would be something that's saying, oh, I think that's the cat, or I think the probability that this image shows a cat is, let's say, 90%. Okay, some hyperparameters. I think we will skip this one, but the important thing is how all those algorithms work. They are taking the algorithm, they are taking the data, and they are basically thinking, okay, I think my algorithm, or I think my model is represented by a super complicated mathematical function with some parameters. So I will pass once the data and try to guess the parameters. Once you guess the parameters, you say, okay, I think now I'm able to compute what we call loss. It's basically pretty simple. I have a function that tells me whether my model is doing good or bad. And it says, okay, let's say I have some data that I haven't seen in the training, and I'm doing the prediction on that data, and I'm computing, okay, the loss is, so I'm not doing very well with my mathematical function with all those parameter settings on the job, so I will adapt those parameters. And every time I adapt those parameters, I have to basically go over the entire data set, and so on and so forth. And that's an iterative process, so there is no mathematical solution where you can derive those parameters somehow. So it's a bit of trial and error. It's smart trial and error process. And there are several possibilities how to do that. You can do that by running once over the entire data set. You can do that by only looking at one example. What is mainly used in machine learning, it's called mini-batch. So basically, you take batch by batch, and every time you update your model. So you take some part of the data, you compute how well your model did based on that data, and you iterate and iterate, iterate. Epochs is something that's just basically, that's saying, if I take the mini-batches, then how many steps do I need to do before I have seen the entire data set? Okay, so how do we know that the model is doing well? Because we can test the model on data that the model haven't seen so far. So in our example, when we want to predict whether the image is showing a cat or a bird or whatsoever, we are saying, okay, we have some actual values, so we know that this example is a cat, and I'm predicting, and I'm basically, for every prediction that I've made, I'm checking whether that was a correct prediction or not correct prediction. So you have a table that's showing you, so if you have actual class as a cat and your prediction is a cat, then it's great, because that's your algorithm did well. If its prediction is non-cat, then you count basically how many predictions are okay, how many predictions are not okay. And for every combination of that. So oftentimes people are reporting on accuracy. Accuracy means you take all the predictions that went well, so you predicted well, and divide that by all predictions. The problem with accuracy is if you have several, so if you have data set that, let's say you want to predict if something is a cat or is not a cat, and in your data you have like 99% of the images are showing a cat and only 1% is showing a dog. So if you predict always, I think that's a cat, then you have 99% of accuracy. And that's why you should, always by multi-class. So you are trying to predict multi-classes. You are always looking at the, every class whether the prediction is fine or not. So the terms that we are using is recall and sensitivity. So precision means that how many of the well-predicted value are in the set and whether I managed to cover all the ones that are in the subset of the data. Okay, so let's go to the frameworks very quickly. TensorFlow is a framework designed in Google Brain. It's open source. It's widely used. It's under Apache license. Keras is another thing that's developed in Google. That's basically developed by one engineer in Google. So he said, OK, I want a high-level API on the existing libraries. The existing libraries can be not only TensorFlow, but also other libraries. Then you can iterate faster. It has all building blocks for computer CNN, so convolutional neural networks. RNNs are used for neural networks used for text recognition. And it has all the high-level concepts, meaning it has the layers, activation functions, optimizers, and tools for iterating over the data. Horovod is developed originally at Uber, and it's yet another layer how to run distributed training. It runs on TensorFlow, Keras, PyTorch, MXNet, has support for CPUs, TPUs, and GPUs, and since a year it's hosted by Linux AI Foundation. Okay, great. Let's go to the live example. So I hope this will work as well. Can you switch to my computer? Oh, great. OK. So when you click on, when you go to your AWS account and click on SageMaker, that's basically the landing page. That's what you will see. You will see all the building blocks that I've spoke about, so notebooks, training, inference. The one that I haven't touched today is the grant truth. That's another newly released building block. It's meant for if you have data, but you don't have labels for the data, that will help you to label the data. So it has a connection to Mechanical Turk, so you can pay people to label your data. OK, so let's go to the So that's something that I have open. Let's go to the notebook. So my notebook will be trying, so I will learn a CNN model to try to categorize the data. So I will divide the data, how it is divided in CIFAR-10. So I will be having 50,000 of data points from all the 10 categories. I will not make the pictures bigger because it's a lot of pixels. You will see it's only 32 times 32, red, green, blue. So it's colored data. And let's go with the setup. So how we set up? We basically say, OK, what we need a role, so we need to know, all the permissions that we are using. We are just preparing a S3 bucket where we put all our data. We will, from the data, so you see that so I'm cheating a bit because that's already executed. So those cells are executed because the training takes a couple of minutes, so I don't want you to wait for it. But what you do here is you take the data from the CIFAR-10, you unpack the data, and you transform it to TensorFlow data format. So that's how the TensorFlow is using the data. That's yet another packaging thing for having the data distributed. And I'm uploading my data. So what we need in SageMaker, we need the data in our S3 bucket. So this step is important. I have to have the data in my S3 bucket. I have a small Python script. This one is, I hope you can see this one. Can you see the lines? And yeah, great. So that's basically how you build your model. That's all what you need to build your model. You are specifying, so you don't need to understand every line, but let's say here one, you are specifying a convolutional layer. You are saying that 32 is the number of the filter, so a filter for detecting an edge, detecting a hand, detecting an eye. You are saying the size of the filters. Commonly used size are 3 times 3. Batch normalization is only bringing the data points into the same scale. Activation function is making, so what in neural networks, they are all those layers stuck together. So you multiply the input with some weight and you add all those numbers together. If you will end up with this, you will have a linear function. Linear functions are great, but they are not super powerful. That's why in neural networks, you are using activation function. It's just a function that's put on top of the linear function that makes it nonlinear. And with nonlinear functions, it's possible to predict values or to have models that are way, way more powerful than linear models. So you can stack, so you have here one layer, then you stack another layer with some models, and then you do the subsampling. Max pooling is taking the maximum of the frame, and regularization of a dropout. Dropout is a function, regularization function, that helps you not to overfit, not to adapt too much to the training data set, and it's just randomly deleting some edges from the graph. And that works. So basically that is. So the 0.2 is saying the probability of deleting an edge in a graph is 20%. So you do basically the one block, then the second block with some other sizes, but the same activation function, the same batch normalization. You do the same thing for the third time, and that's the end. So that was what was in my picture. You flatten everything. So before you have like data in three-dimensional space, then you do like one-dimensional space. You connect it with densely, which means fully connected layer. You create 512 new nodes. You connect everything with everything. You have some dropout, and then activation function softmax. It's used for classification of several classes. That's also like mathematical function, not super important. Okay, how do we distribute that? Pretty easy. So we create an estimator, TensorFlow estimator. We say we are using the train Python script, and we are saying, okay, hyperparameters are something. We have instance types. So for this example, we use P3 8x large as GPU instance. Then we say the distribution, that's the horovod part into it. So you are saying, okay, I will have so many processes per host. The 4 that you are seeing here is the number of GPUs on every machine. And we will be taking 2 machines. And the last step is just basically fit, means train the model. And after 7 minutes, you have trained the model. You have the model already there. So the last step, I will skip the online inference. I will do the batch prediction. So the last step is, when you have the model, you want to push the model so that you can make predictions with that model. So what you need is some transformation, how the model will read the data from your S3 bucket to do the prediction. That's an input. So here, it's only a couple of lines saying, basically creating a JSON. That's what the API, TensorFlow API, is expecting. The output handler is doing basically nothing, passing the data. You specify the libraries and the dependencies that need to be included, and you can create the model. So you are saying, I want P3 2x large instances. The model is already estimated, so I get the estimation. I have all the permissions in the execution role, and that's it. So basically, you have the endpoint, and you can run your transform data. So here we will have the 100 concurrent jobs with 2 instances of the P3 2x large data, and that's how we feed our data. When that's done, So the transformer has an output. We take the output, we download the data in our S3 bucket or in our notebook, it doesn't matter. And this short script is doing basically checking what is the output of the model and combine it with the label, because we have the label for the 10,000 data points that we haven't used in the training. And here is the output. So I've calculated the accuracy. So on 10,000 data examples, we have accuracy of 86%, which is kind of good. And we have confusion matrix, which is saying, okay, actually it's an L plane. The prediction, it's an L plane. The probability, or the number of examples on my 10,000 is 90%. So on the diagonal, you will see basically what is the probability of the proper prediction on your model. And that's it. So basically you run your model on data that you download from the internet, that you stored into S3 bucket, transform it into TensorFlow data format. Then you specify the algorithm, you specify the instances that the algorithm is running on, and once the estimator, so once the model is created, you push it for the inference, and the inference is done. You test it with your data. That's all. So that's also all what I wanted to show you today. Thank you very much. And